I welcome you to the ASM online tutorial. In this video, we talk about lock-in thermography for the application in microelectronics failure analysis. It's a slightly converted version of the tutorial that will be held at ISTFA. My name is Sebastian, and I'm with the Fraunhofer IMWS in Halle, Germany. A few words of the topic before I start the tutorial. In microelectronics failure analysis, we employ lock-in thermography to localize thermally active regions that indicate resistive defects. Such defects can be resistive shorts between metal lines, between contacts, bumps, pins, etc. It can be oxide breakdowns. It can be locally increased metal or polysilicon line resistances or increased contact resistances. In any case, we have to have an ohmic defect in which electrical power is converted to thermal energy, and that leads to a local increase of the temperature. That's the outline of the tutorial. It's split into 4 blocks. I will start with the principles of direct thermal imaging, continue with the basics of lock-in measurements, show you the experimental setup of the lid system that we have here at the Fraunhofer, and close with a few case studies on packaged devices where we used lock-in thermography for localizing resistive defects. So what is direct thermal imaging? It's a contactless method to capture the thermal radiation that has been emitted by an object. The image on the left here shows the intensity distribution of the thermal radiation of a building based on its local temperature. The IR radiation has been emitted off the surface of the building and then propagated to the detector of the camera. If you illustrate the scenery in which we commonly measure, we have the sample, which is shown here on the left-hand side. We have the atmosphere through which the thermal radiation needs to propagate. And we have an IR-sensitive camera with an optics. So on the way from the sample to the camera detector, the thermal wave needs to propagate through this atmosphere, which we will first have a look on. And this graph down here, we see the atmospheric transmission of electromagnetic radiation in the infrared range at 20 degrees Celsius and 100% relative humidity. We see 3 major windows, which are the short range, mid-range, and long-range window. Lock-in thermography and failure analysis we do in the mid-range window, which ranges from 3 to 5 microns. The detector material that is commonly used is indium antimonide with the sensitivity curve shown here. Okay, now let's have a look at the sample and the relationships between the sample properties, the temperature, and the irradiated thermal energy. Before I start, I would like to introduce the term of black body radiation. Black body radiation describes an idealized generalization of the irradiated energy. It means that the black body absorbs all incident energy, that all absorbed energy is emitted, that there is no transmission through the object, and no reflection at the surfaces. The intensity and spectral distribution only depend on the object's, on the black body's temperature. There are 3 formulations that can be used to describe this radiation behavior. It's Planck's law, Wien's law, and Boltzmann's law, and I will go through all 3 of them. The first one, the Planck's law, describes the relationship of the radiated thermal energy as a function of wavelength and temperature. You see here different curves which were computed for different temperatures. The formula is given here, which means that if you know the temperature of an object, which in our case here has to be a black body, you can compute the spectrum, the transmission spectrum in the infrared range. Then the next one is Wien's law. It describes the relationship of the wavelength at maximum amplitude to the temperature. If you look at these curves, you see that the maxima are shifted towards a smaller wavelength. it's an inverse characteristics or behavior that you see here, that the wavelength at maximum intensity decreases with increasing temperature. And last but not least, it's the Boltzmann's law. It describes the relationship of the irradiated energy to the temperature, and we see that this relationship is described with a power of 4 to the temperature. These curves show the total radiated energy of an idealized black body. In order to obtain the emitted energy of a real object, we need to relate these idealized values to real values. And that's done by using a scaling factor, which is called the emissivity, which you see in this formula here. So the emissivity of a black body is 1, and it decreases for real objects. So the impact of this emissivity is illustrated here. The object that is shown in this graph was imaged at a homogeneous temperature, was sitting at room temperature for a while. So we can assume that there is no temperature gradient, that it's like the entire device was at room temperature. So if the amount of thermal radiation would only depend on the temperature, we wouldn't see anything. However, there is contrast in this image, and it's the contrast that arises from the different emissivities of the individual structures. The emissivity of an object depends on the material itself, on the surface quality, particularly the surface roughness, the temperature, and the wavelength. As a rule of thumb, we can say that metals exhibit a low emissivity between 1 and 5%. Silicon is transparent. It exhibits a medium emissivity of approximately 10%. And glass and molding compounds have a high emissivity of above 90%. For opaque samples, it can be said that the emissivity is equal to the absorption coefficient, and it should also be noted that the emissivity can change during the experiment, for instance, due to an increase in temperature or through thermal degradation of, for instance, metal lines. The message that should be taken home from this slide is that even unpowered ICs may show a strong infrared contrast, which is, however, a pure emissivity contrast. This, like for thermal measurements of temperature-related effects, this emissivity needs to be compensated for. As quite simple calibration or normalization method would be to record a calibration image of the sample at room temperature, and then divide the local emissivity, or divide the recorded IR images by this reference or calibration image in order to correct for this local emissivity. So that would lead to that image that is shown on the lower left here. So we would have a homogeneous distribution of the temperature, and no emissivity impacts the contrast here. And if we now turn on the sample, if we power it, then we will see a contrast, which is shown on the right-hand side here. And that contrast arises from an increase in temperature due to the operation of the sample. That would be a rather simple way of calibrating the or compensating the emissivity. If one wants to measure actual temperature values, absolute temperature values, the calibration has to be carefully done, and it needs to address not only the emissivity of the sample, but also the system transfer functions for the individual temperature range that should be, or that are to be investigated. Okay, that much about the direct thermal imaging, the fundamentals of the direct thermal imaging. And I'll continue with some basics to about the lock-in measurements. As I've mentioned before, in lock-in thermography, we are looking at resistive defects which are caused by, or which cause a local increase in the temperature, which is based on like metallic resistive shorts of metal lines, increased interconnect resistance, or oxide breakdowns, or like anything else that is based on an ohmic defect. However, in microelectronics, we usually just like induce microwatts of power, and these microwatts of dissipated power typically correspond to temperature increases in the microkelvin range. However, the sensitivity of the camera is above 10 millikelvin. Steady state imaging wouldn't be applicable as the strong T saturation would lead to a shadowing of small hotspots, and buried defects from inside the package would only lead to very small temperature gradients at the surface of the sample. So the solution will be, or is, lock-in amplification to increase the sensitivity of the thermal imaging. So the approach is aiming at the extraction of a weak signal from the noise floor. And in our case of lock-in thermography, we inject a small thermal signal into the sample at a fixed repetition rate. That leads, or that provides us with a narrowband signal. And it allows us to average, since we repeat the measurement over and over again, and the averaging allows us to eliminate statistical noise. So we're not looking at a static signal, but at an alternating signal, which follows our excitation, and we are able to perform sequential averaging and correlation to the excitation signal. So that would be a schematic of a lit system. We have the sample here that is excited by our power supply. It's a source and measurement unit. And the excitation looks similar to this. We basically just turn on and off the sample. This SMU is synchronized to the infrared camera, which captures the images. So for each cycle, a number of thermograms are recorded, and then the pixels at each pixel we do a correlation with the excitation function, or with a sign that is in phase with the excitation function, and that allows us to compute an amplitude and phase. Let's now have a slightly closer look into the signals. Let's assume our blue signal here is our measured signal, and the red curve is a sine wave which is in phase with our excitation, which means it's 0 at the beginning and then continuously moves on. And we have the black curve here, which is the cosine to our excitation, which means it's shifted by 90 degrees to the sine. If we now modulate our measured signal, our blue signal, with the sine and the cosine, we obtain the curves down here and that graph. We have our measured signal in blue again, and we have the red curve, which is the sine modulated, and the black curve, which is the cosine modulated. And we now integrate over a period of our excitation, then we obtain an S0 component for the correlated signal, or for the modulated signal that was modulated with a sine, and an S90 component for the signal that was modulated with a cosine. If we have a closer look to this simple formulation here, we see that's a correlation that we actually perform here. So from the S0 and S90 values, we can compute an amplitude and a phase, which is commonly used in lock-in thermography to express the thermal, or the amplitude and phase of the thermal signal. Let's have a look at a signal. It's an artificial signal that was computed in MATLAB. It contains a 1 Hertz sinusoidal signal that was shifted by 25 degrees. And there was noise added with an amplitude of 20 times the amplitude of the sinusoidal signal. Can you see the signal? Probably not, so I help. Here, now you can see it. And if we now perform the lock-in amplification, this is a movie which I will start in a second. And we have the noisy signal here, and you will see that over time, as the lock-in amplification is performed, over time the signal-to-noise ratio will increase. You will be able to see the signal itself. And we will also see, if you look at this value down here, that the phase estimate of that computed, of that noisy signal will be quickly very close to the simulated value of 25 degrees. So I start that now, and you see that immediately after starting, we will soon have an increased signal to noise ratio. And the value down here, which was like 2, I think, at the beginning, is already like close to the like actual value of 25 degrees after a few hundred cycles. That's the number of cycles for repetitions of the actual lock-in measurement. So if we now look at the red curve, which shows the signal to noise ratio as a function of the lock-in periods, we see that we have a quick increase at the beginning and then reach some kind of saturation where it increases with a much slower, much smaller slope. So we also see that after 400 lock-in cycles for our signal, where the noise was 20 times as high as our signal, that the phase deviation is close to 0 already after 400 cycles. Okay, that's an image, or these are images of the lock-in system that we have here at the Fraunhofer in Halle. We have the infrared camera here. We have a tilt stage for the sample. We have probers in case you can't solder wires to your sample. If it's too like filigrane or small, you need to like connect the electrical the power supply using needles, like needle probers. It's an XYZ stage for precise positioning. Yeah. So again, from what I've explained before, the system, the lock-in system, captures the images, and then together with or in synchronization with the power supply, these images are correlated with the sine and the cosine, and the system will provide a 0-degree image and a 90-degree image. That's the outcome. From these two images, as I've shown before, we can compute the amplitude graph and the phase graph. The amplitude basically describes the similarity of our signal at a certain pixel with our excitation, and the phase describes the delay between the signal trace at a certain pixel and the excitation. So we can see that even small hotspots can be nicely detected and resolved in the amplitude image. And if we now superimpose that on the emission or topography image, we can nicely navigate to our defect and find its position. That's in sum all the graphs that are involved in this lock-in process. So we have the topography image. At the beginning, we compute the in-phase and out-of-phase image. Then we compute the amplitude and phase image, and we can normalize them to each other to provide or to obtain a higher spatial resolution and compensate for emissivity. Another effect I would like to mention is the comparison between steady state investigations or the thermography and lock-in thermography. In steady state, you would basically, even if you compensated for your emissivity, you would basically just like turn on the power and would look at the signals, the thermal radiation signals that are irradiated off the sample. And in lock-in thermography, as you have learned, we turn the sample on and off and only follow the transient signals that are related to our excitation. So in the steady state imaging, the contrast would be governed by the local emissivity and the heating of those structures that would prevent us from detecting small sources. And in lock-in thermography, we can even detect small and weak hotspots with an improved lateral resolution. I've mentioned that in lock-in thermography, we inject the thermal signal, which is basically at the beginning the electrical signal, into the sample at a fixed rate. And this rate is important to the outcome. So if we would inject or excite the sample at a low repetition rate, that allows the thermal signal to spread, and we would also inject way more energy than in cases where we have a higher frequency. Here, the injected energy is limited. It's much smaller than at lower frequencies. And also, we do not allow the thermal energy to spread as far as it is possible at a lower frequency. The effect that's observed here is thermal spreading, and this is related to the thermal diffusion length, which depends on the material and the excitation properties, and of course the wavelength. That's another example where we've looked at a packaged molded device, and we have analyzed the signals at multiple frequencies. So we've looked at 1 Hertz, you see a rather large hotspot, and once we increase the frequency, we can see that we can nicely resolve the hotspot with a much better lateral resolution. Okay. So far about the lock-in thermography or lock-in amplification. I'll come to the last section of the tutorial, in which I would like to show you a few case studies of lock-in thermography on packaged devices. In packaged devices, or when we investigate packaged devices, there's usually no direct optical access to the IC and the interconnects which are within the package. However, the heat propagates through these opaque layers and reaches the device's surface, where it's irradiated off towards the camera. And that allows us for a non-destructive through-package hotspot localization. As I've just shown on the previous slide, the lock-in frequency, however, allows, lower lock-in frequencies allow for higher signal-to-noise ratios, but less lateral resolution due to thermal spreading. So there's always a trade-off, which means that for an unknown sample, you always need to do some sample-related optimization in order to get the maximum information out of your analysis. Case study 1 looks at a packaged device, and we have observed a weak hotspot. And after chemically removing the molding compound, this short between 2 wire bonds were found, and that correlated nicely with the hotspot. And the second case study, the second example, it was also addressing, or it's also addressing a fully molded sample. At the beginning, lock-in thermography was applied, and there was a diffuse hotspot observed. However, the resolution or the diffusion or the size of that hotspot didn't really allow localizing the defect, which is why we thinned back the molding compound and repeated the lock-in thermography, and with much thinner layer, with a much thinner layer of the molding compound, we've actually had a chance to nicely localize that defect. And then cross-sectioning revealed that there was a flitter particle between, shortening these 2 wires. You see in that plane that there are of that flitter particle, you see some points, and that was just placed in here to give you an idea of what this flitter particle must have been looking like. The third case study that I want to show you looks at also a packaged device which was already open. So you see the IC structure here, and doing lock-in thermography, we've observed a hotspot outside the chip in the molding compound. So we further thinned the molding compound, which required removing the chip. We got a much nicer, much clearer idea of that hotspot. We see a path here, and we see a hotspot here. We've then used our plasma FIB in order to prepare a cross-section here, which was then imaged in the electron microscope. We've observed this this inclusion here and doing EDX analysis on this inclusion, the presence of aluminum and titanium was revealed. So that must have been a particle or an inclusion, a metal inclusion that came into the package during the molding process. Okay, that takes me to the end of the tutorial. I quickly want to summarize what I've said. LIDIS, Lock-In Thermography, is employed for localization of resistive defects in microelectronics. Device under test is periodically excited, which means that it's basically powered on and off. The thermal radiation that is irradiated from the surface of the sample is captured through direct thermal imaging using an IR camera, and the measurements are repeated at a fixed repetition rate. And at each pixel in the image, the signal traces are correlated to the excitation signal, which is basically the lock-in amplification, and that provides an amplitude and a phase image. And this approach of lock-in thermography and failure analysis allows us for the detection of extremely small defects in electronic components on wafer, chip, and package level. Thank you.